Hello, future AP Chemers. Welcome to AP Chemistry. Hope you're having a wonderful summer so far. We're going to do a little bit of notes and hopefully it's all review for you. You have received the chapters 1 and 2 study guide, which is basically a packet that has all the guided notes for you for those two chapters. At the beginning of each study guide, similar to last year, you had learning objectives. So here you have something called essential knowledge and learning objectives. And so College Board, they are the ones that designed the AP Chemistry curriculum. They came up with 6 big ideas to describe the material you need to know for AP Chemistry. And those 6 big ideas will be given to you on the syllabus on the first day of school. They then divided each big idea into essential knowledge and also science practices. So those are what you need to know essentially. There are a few sentences they kind of explain what you need to know. And then those are broken down further into learning objectives. And so I highly recommend that at the end of the chapter and also in April, when we're done with the curriculum, you want to look at the list of learning objectives and kind of check them off to make sure that you know each of them. So we'll start here with chapter 1. When you get your textbook, you'll see that chapter 1 is kind of an introductory chapter, and then at the end, it has a Let's Review section that talks about measurements and sig figs and scientific notation and all that. And we'll start with sig figs. So significant figures are used to help us, when we look at a number, know how precise the measuring equipment are. So we're always limited to our measuring devices and how precise they are. We always try to come up with more precise equipment. And so the significant figures help us with that. There are 3 things that you need to know with sig figs. You need to know how to measure things when you go to the lab and record them to the correct number of sig figs. You also need to be able to tell how many sig figs a number has when you look at it, if it was already measured for you. And then finally, when you do calculations, you need to be able to record your answer with the correct number of sig figs. So we will start with, when you go to the lab, how do you measure and record numbers with the correct sig figs? So if you have graduated devices, so they have like little lines, little increments, what you do is you look at the smallest increment that you have lines for. And you record that down and then you estimate 1 extra. For example, here's a graduated cylinder. We're missing our units here, so these are in units of milliliters, both of these. So if you look at the lines here, the smallest lines are every 1/10 of a milliliter. And so what you do is you estimate 1 extra, and so you record your answer to the 100ths of a milliliter. So for example, in that first one, I can tell for sure that it's between 5.4 and 5.5 milliliters. So the 5.4 is what I know for sure, so I record that down. And then I estimate 1 more, so I'm going to say maybe 5.46 milliliters. It is understood that that last digit is an estimate. So if they ask you on the AP exam, for example, to record that value, they'll accept probably anywhere between 5.44 to 5.48 milliliters. Let's look at the next one. Looks like, those 2 pictures overlap, but this is the 20 milliliter line. This is 30, this is 40. So it looks like it's between 25 and 26. So we know for sure that it's 25 point something. The smallest units or the smallest increment or lines there are every 1 milliliter. So that means you measure it to the 1/10 of a milliliter. So I know for sure that it's 25, between 25 and 26. And it looks to me like it's closer to the 25 than it is to the 26. So I'm going to say 25.2 or 0.3 milliliters. Okay, next one, I have a ruler and it's in centimeters. Looks like my little lines are every 1/10 of a centimeter. So that means you want to record it to the 100th of a centimeter. And it looks to me like it's right on the 5 line, the 5 centimeter line. So I know for sure that it's 5.0, so I'm going to estimate one more. I'm going to say 0.00 centimeters. So for this one, they'd accept 4.99, 5.01. Any of those would be okay. All right, next we want to be able to look at a number and tell how many significant figures it has. So whatever way you prefer to do this is fine. If you remember the 5 rules that you had in physical science, most of you had them split up as 5 rules. You can use those. If you want to use dot right, not left from last year, if you took honors chem, you can use that, whatever you prefer. I'm going to go over the 5 rules. I'm also going to go over dot right, not left, and you pick which way you want to do it. So if you're going with the 5 rules, the first rule says that if you have a non-zero digit, it's always significant. Non-zero numbers are always significant. So, for example, let's say that you have 523 centimeters. None of those are zeros. They're all non-zero digits. So that tells you that they're all significant, so that would have 3 sig figs there. Well, what if you have a 0 then? If you have a 0, you look at whether it's leading or in the middle or trailing. Leading zeros are never significant. So for example, let's say you have 0.012 grams. These zeros are leading. They come before the numbers, and so those are not significant. So the only sig figs here are those 2, so that's 2 sig figs. What if your zeros were in the middle? We call those captive zeros. Captive zeros are always significant. For example, let's say you have 508 milliliters. So the 0 here is trapped. It's captive between 2 non-zero digits, so that means it's always significant. So all 3 of those are sig figs. So we have 3 sig figs here. Trailing zeros are the tricky ones. Trailing zeros are sometimes significant and sometimes they're not. Trailing zeros are significant when there is a decimal point. For example, let's say I have 95,000 meters. I can write it this way or I can write it this way. If you have a decimal point, like here, then that makes the trailing zeros significant. So those are all significant, so this number would have 5 sig figs. If you do not have a decimal point, then the trailing zeros are not significant. So that means those are the only significant ones, so that is 2 sig figs. Last rule, rule number 5, says that exact numbers are infinitely significant. Exact numbers include counting numbers and defined numbers. So, for example, if I'm in a classroom and I count that I have 21 students, I can't have 21.5 students, I can't have 21.02 students. I counted 21 students, not 25. I counted 21 students. So counting numbers are infinitely significant. I have exactly 21 students. I can never have a fraction of a student because I counted it. So that number would not be 2 sig figs, it would be an infinite number of sig figs. Also, defined values are infinitely significant. For example, by definition, 1 meter, 1 meter is equal to 100 centimeters. That's by definition. When they came up with the prefix centi, they said that's 100th of a meter. And so by definition, that would not limit your sig figs. So that 100 or that 1 is not limited in sig figs. Now, not all conversions are defined values. For example, 1 inch is 2.54 centimeters. That is not defined. That is a measured value. So they took an inch, and they took a centimeter ruler, and they measured how much an inch is in centimeters. And they recorded that to be 2.54. That is measured, that is not defined. So only defined values are infinitely significant. Now, if you don't want to remember all 5 rules, you can, instead of these 4 rules, say dot right, not left. That's what we learned last year, I think, if you took honors chem. And so what that means is if you have a dot, you start at the very right of the number, and if you're at the right of the number, then the only way you could go is left. So you start at the right of the number, and you go all the way to the left until the last non-zero digit, and everything from where you start to where you end is significant. For example, let's say you have 0.5320 meters. So if you have a dot, that means you have a decimal point, which you do in this case. Then you start at the very right of the number, so right here. And you go to the left until you reach the last non-zero digit. So the last number that's not a 0 would be that 5. So you go all the way to that 5. From where you start till where you end, those are all significant. So 1, 2, 3, 4, 5. So this is 5 sig figs. If you don't have a dot, so you don't have a decimal point, then you do the same thing, but you start from the left. So if you have a dot, you start from the right. If not, then you start from the left. So for example, let's say I have 90,500 centimeters. So if you don't have a decimal point, you start from the left this time. So you start from that 9. And you go to the right, because you start from the left, so the only way you could go would be to the right, until you reach the last non-zero digit. So the last non-zero digit there would be a 5. And so you go there. And so from where you started to where you ended, those are all significant. And so in this case, I have that 9, the 0, and the 5, so that would be 3 sig figs. So if you don't want to remember all 4 of those rules there, you can just remember the dot right, not left. So let's go back after doing this then to looking at those numbers at the top here and trying to figure out how many sig figs they have. Okay, so we have 40.150 grams. So I'm going to use the dot right, not left rule. So this has a dot in it, so I'm going to start with the right. So that's 0, and I'm going to go to the left until the last non-zero digit. So that goes from the 0 all the way to that 4, and so that is 5 sig figs. Let's look at the next one. It says 100 meters is equal to 1,000 millimeters. Both the 1 and the 1,000 there are infinitely significant because it's a defined value. Okay, next one is 4,050 milliliters. So I'm using the dot right, not left. So since it doesn't have a decimal point, I'm going to start from the left. And I'm going to go until I reach the last non-zero digit, which is that 5. So I'm going to stop here. So that's 1, 2, 3. So that is 3 sig figs. Last number there is 4,000 kilometers. That does not have a dot, so I'm going to start from the left, and that's where I stop. There are no other non-zero digits, so that is only one sig fig. If you do it with those rules 1 through 4, you'd still get the same answer. So we looked at measuring, we looked at figuring out how many sig figs in an already measured number. Now we're going to look at mathematical operations. Addition and subtraction are similar, and then multiplication and division are similar. We'll start with the addition and subtraction. So the rule for that one says that the result has same decimal place as the least precise number used in the calculation. So what we care about here is decimal place. So for example, let's say I have 12.11 centimeters. I'm going to add to that 8.0 centimeters and then 1.78 centimeters. So when I add those up, I get 89 centimeters. That's my total. I can do it in my head, or you can do it in a calculator. Then you need to round it to the correct number of sig figs. So what you do is you look at the numbers that you're given, those three numbers that you're adding together, and you go with the decimal place that's in your least precise number. So that first one is precise or significant to the hundredths of a centimeter. This one's to the tenth of a centimeter. This one's to the hundredths of a centimeter. So that middle one to the tenth place, that is less precise than the hundredths place. So your answer should be to the tenth place. So it is 21.9 centimeters. Let's do another one. So let's say you have, let me use a different color, 1.1 times 10 to the 6 milliliters plus 800 milliliters. Now, if you are given something in scientific notation and you're adding and subtracting, you have to write it out in longhand so that you can figure out your sig figs. That 1.1 times 10 to the 6 milliliters is 11,000,000 milliliters. And then you have 800 milliliters. I like to line them up. So when you add those, you get 11,000,800 milliliters. So if you look at the top number here, this is only precise to the hundred thousands. This is only precise to the hundreds. And so this is less precise, and so your answer would round to 1100,000 milliliters. Multiplication and division. So in multiplication and division, we don't care about the decimal place. What we care about is the number of sig figs. So the result here should have the same number of sig figs as the least precise number in the calculation. So what we care about here is the number of sig figs. So here we care about the number of sig figs. Here we care about the decimal place. So for example, let's say that we have 4.56 centimeters times 1.4 centimeters. If you punch that into your calculator, you get 6.381 centimeters squared. So this number has 3 sig figs, this number has 2 sig figs, so your answer should have only 2 sig figs. So then that would round to 6.4 centimeters squared. So again, with multiplication and division, what we care about is the number of sig figs. For addition and subtraction, what we care about is the decimal place. There's a little video that I posted on Google Classroom. I think it's called Where the Heck to Round by Mark Rosengarten, and it kind of goes over those 2 rules here if you'd like to see it. Let's do an example. It says, what is the volume of 14.25 grams of alcohol if the density of alcohol is given to us as 0.70 grams per milliliter? We want to express the volume in both milliliters and cubic centimeters. So since we're given density and we're given grams and we're trying to find the volume, you can use the density equation. So D equals M over V. Our density is given to us as 0.70 grams per milliliter. Our mass is given to us as 14.25 grams. And V is what we're solving for. So you can cross multiply 14.25 divided by 0.70. You punch that into your calculator, and then you round it to the correct number of sig figs. So let's figure out how many sig figs we should have. This is division. So we go with the number of sig figs as opposed to the decimal place. And so this one has 2 sig figs. This one has 4 sig figs. So it should be 2 sig figs. So after you punch it in, you'd get the volume is 20 milliliters. It also wants the answer in cubic centimeters. So we're going to say we have 20.0 milliliters. Then put milliliters on the bottom, centimeters cubed on top. 1 milliliter is equivalent to 1 centimeter cubed. That's by definition. And so that's 20.0. That does not limit your sig figs. Centimeters cubed. A little note about sig figs on the AP exam. So obviously on my test I'm going to be strict, and my homework I'm going to be strict with sig figs just like we were last year. But on the AP exam, on most questions, they will accept plus or minus 1 sig fig. And there's a little box on the previous page that talks about that. So for example, let's say your answer should be 3 sig figs. So if you record your answer as 2, 3, or 4 sig figs, they will accept that on most questions. The only exception to that is if the question, the point of it was to figure out how many sig figs, then they will not accept it. So every now and then they'll have a sig fig question on there. They won't tell you which one it is, where they will only accept the correct number of sig figs, but on all of the rest of the exam, they'll accept plus or minus 1. And so if you're not sure, or if you don't have time on the test because you're kind of in a hurry and it's a long test, what I recommend is do 3 sig figs, because 3 sig figs will cover, if your answer is 2, 3, or 4 sig figs, then 3 sig figs would be acceptable. There are very few answers that require 1 sig fig, and there are very few answers that would require 5 or more sig figs. So if you put 3 sig figs, that covers you for 2, 3, or 4, and that would be most of your answers. So ideally you would want to figure it out, but if you don't have time, just go with 3 sig figs. Alright, next topic is metric conversions. And so with metric conversions, we have our base unit. Those are the ones that don't have any prefixes before the unit itself. So those would be meters, grams, and liters. And then instead of, using numbers that are really, really big or really, really small, like for example, if you're talking about the number of particles, the number of atoms, in a sip of water, that would be a really, really big number. Or if you're talking about the mass of an atom, that's a really, really small number. So we use metric prefixes, kind of like scientific notation, to help make our numbers manageable or reasonable to look at. And so we put these prefixes that kind of mean that you multiply your number by some kind of factor. So those factors are always 10 to some power. So if it's 10 to the 0, which is just 1, then you're at your base unit. So let's look at the left side. If you multiply your number by 10 to the 1, that is called a deca. And its symbol is capital D. So for example, if you have a decameter, that means you have 10 meters. Next is 10 to the second, which is a hecto. That's an H. So if you have a hectometer, that means you have 100 meters, 10 to the second. Next we have 10 to the third. That one you should be familiar with. That's a kilo, which is okay. So if you have a kilometer, that means you have 1,000 meters. We'll jump to 10 to the sixth. That's a mega, which is capital M. So if you have a megameter, that means you have 1,000,000 meters. 10 to the ninth is a giga, capital G. So a gigabyte, that means 1,000,000,000. And then 10 to the 12th is a tera, capital T. On the other side, to the right, that gets smaller, so 10 to the negative 1, that would be a deci, lowercase d. So if you have a decimeter, that means you have 1/10 of a meter. 10, I'm sorry, that's a negative there. It's hard to see it. 10 to the negative 2, that is a centi, lowercase c. So if a centimeter, that means you have 100th of a meter. Next is 10 to the negative third. That's a milli, lowercase m. So if you have a millimeter, that's 1,000th of a meter. Then we have 10 to the negative 6. That's a micro. I'm sorry, that should say micro. And its symbol is the Greek letter mu, which sounds like an M, but it looks like a U. 10 to the negative 9 is nano, with an N. 10 to the negative 12 is a pico. 10 to the negative 15 is a femto. And so on. So let's try these. It says convert 0.0537 centimeters to meters. So what you do is you write down the number that you have. So 0.0537 centimeters. You do a conversion factor. A conversion factor is a fraction where the top and the bottom are equal to each other. So the conversion factor itself is equal to 1. So when you multiply the number by 1, it's equal to itself. So it should be equivalent. So that's why you're allowed to do that. So you're going to put centimeters on the bottom so that you have the same units on top and the bottom so they could cancel each other because we don't want centimeters anymore. On top, you put the units you're looking for. So in this case, we're looking for meters. So I'll put meters here. And there are many ways to do this. So if you already know how to do it, go with the way that you know. If you don't, then you can use this way. So what you do is you put a 1 next to the unit that is larger. So between a meter and a centimeter, meter is larger, so that gets a 1. And then the smaller unit gets a 10 to some positive value. It's always going to be positive. And to figure out what that value is, you look at your two units and you see what the difference between them is, and you put that as a positive value here. So meters, the base unit, that's 10 to the 0. Centi is 10 to the negative 2. So between -2 and 0, the difference is 2. You put the positive difference. So anything on top you multiply, anything on the bottom you divide. So centimeters with centimeters cancel, you end up with meters. So this is 0.0537 divided by 100 basically. So it is 0.000537 meters. You should be able to do this in your head. On the AP exam, it's divided into 2 sections. There's a multiple choice section and a free response. For the multiple choice, it does have some math, but no calculators are allowed. So they expect you to be able to do some simple math like this in your head. You should be able to tell that if you're dividing by 100, you move your decimal place to, or your decimal point 2 places. Let's look at the next one. We want to go to nanometers this time. So we still have 0.0537 centimeters. We're going to do a conversion factor on the bottom. We want centimeters, so they cancel. On top, we want nanometers, because that's what we're looking for. Between centimeter and nanometer, centimeter is a bigger number, so that gets the 1. The nanometer gets 10 to some positive power. To figure out what that power is, you look at the centi. Centi is -2. Nano is -9, so the difference between them would be 7. So you put 7 there. And again, you should be able to do this in your head. So if we need to move the decimal point 7 places, then you go 1, 2, 3, 4, 5, 6, 7. So that would be 5, 3, 7, 0, 0, 0 nanometers. Or you could do it with scientific notation. So to figure that out, this is 10 to the 7th, so it's 0.0537 times 10 to the 7th. But to make it scientific notation, you need your decimal place to be here, so that's 1, 2. So it's 2 less than that, so it'd be 5.37 times 10 to the 5th nanometers. That should say nano there. Alright, last one. We're going to go to kilometers. So 0.0537 centimeters. Conversion factor on the bottom, put centimeters, on top put kilometers. Kilometer is a bigger unit than a centimeter, so that gets a 1. Centimeter gets 10 to some positive power. To figure that out, you look at the centi is -2. The kilo is +3. The difference between -2 and +3 is 5. So 10 to the 5th. And so again, you should be able to do this in your head. This is 0.0537 times 10 to the -5th. That's the same thing as divided by 10 to the 5th, right? Times 10 to the -5th. So again, there's, if you move it to its scientific notation, move it 2 places, so that would be, instead of -5th, it would be -7. So 5.37 times 10 to the -7th kilometers. If you can't do that in your head yet, you can use a calculator for now, but try to do it in your head and then check with a calculator until you get the hang of it. Let's look at the next conversion. We want to convert a density of 4.85 grams per centimeter cubed to kilograms per liter. So we're going to start with what we have. So 4.85 grams per centimeter cubed. Let's do the grams to kilograms first. So I'm going to put grams on the bottom, kilograms on top. Kilogram is larger, so it gets a 1. The gram gets 10 to some power. To figure that out, here's my gram. Right here, here's my kilo, so 3 is the difference. So put 10 to the 3rd here. That way your grams cancel. Right now I'm at kilograms per centimeter cubed. I'm going to go ahead and do another conversion factor. So right now I'm at kilogram per centimeter cubed. I want to get rid of that centimeter cubed and put a liter. So I'm going to put centimeter cubed on top so it cancels because my centimeter cubed is on the bottom. So I'm going to put the centimeter cubed on top here. And maybe some of you already know what the conversion factor is to a liter. Some of you might not. So I would go to a milliliter first because I know that 1 centimeter cubed is 1 milliliter. So those cancel. And I'm going to do another conversion factor. Now my milliliters on the bottom, so I'm going to put 1 on top. So milliliters on top and liters on the bottom. Between those two, a liter is bigger, so that gets the 1. And then this one gets 10 to some power. Liter is your base unit. Milli is 10 to the negative third, so the difference between them is a 3. That way my milliliters cancel. So now my units work out. I have kilograms per liter, which is what I wanted. Hopefully you can see that you're dividing by 1,000, multiplying by 1,000, so those cancel, so you still get 4.85. Let's look at the next one. It says convert 25.0 centimeter cubed to meters cubed and to deciliters. So I'm going to do it on the top here because I don't have much room. I'm going to write 25.0 centimeters cubed. And I want to convert it to meters cubed. So I'm going to start a conversion factor. On the bottom I'd like to put centimeters cubed, and on top I'd like to put meters cubed, but I don't know the relationship between them cubed yet. So what I'll do is I'll just put centimeters and meters for now. So if I were just doing centimeters and meters, meter is bigger, so that gets 1. Centimeter is 10 to the second here. 1 meter is 100 centimeters. But that would convert it if it was a centimeter to a meter. I want it centimeter cubed to meters cubed. So what I'll do next is I'm going to cube the whole thing. When you do that, the cube distributes. So it goes here, 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 and here. So I'm going to rewrite that. You write it as 25.0 centimeter cubed. And then 1 cubed is 1. Meter cubed would just be meter cubed. 10 squared cubed would be 10 to the 6th. And then centimeter cubed. And so my centimeters cubed cancel. I end up with meters cubed. So you take that number divided by 10 to the 6th. So that gives you 2.50 times 10 to the negative 5th meters cubed. It's 2.5. We also want it into deciliters. So let's do that in blue here. So 25.0 centimeter cubed. I want it in deciliters. Well, I know the relationship between a centimeter cubed and a milliliter. Centimeter cubed and milliliter is 1 to 1. That gets rid of my centimeters cubed, so now I have milliliters. So I'll put milliliters on the bottom, deciliters on top. A deci is 10 to the negative 1, and milli is 10 to the negative third. So the difference between them is 10 to the second. So that gets the bigger, that's the bigger unit, so that gets a 1, and then the milliliters 10 to the second. So 0.250 deciliters. Let's look at the next problem. It says the aluminum in a package containing 75.0 feet squared. What measurement is that? Feet squared. Well, that's a length squared, so that would be an area. So they give us the area. of kitchen foil weighs approximately 12.0 ounces. They give us the weight or the mass. So they give us the area, they give us the mass, they tell us the density, it's 2.70 grams per centimeter cubed. They want the approximate thickness of the aluminum foil in millimeters. This is a lot of conversions. They give us that an ounce is 28.4 grams. On the AP exam or on my test, you'd also be given feet in order to change it to meters or centimeters or something like that. So let's look at what we're trying to figure out here. So we have a piece of foil. And if you had me last year, you know I can't draw. So let's say it's a piece of foil here that is a rectangular piece of foil or something like that. They give us the area of it. So the area is the length times the width. They give us the mass of it. They also give us the density. And we want to figure out the thickness. So basically the height of it. So let's see what we can do. Well, we know that if they give us the density, we know that the density is mass over volume. If it's a rectangular piece of foil, then the volume is length times width times height. Height is your thickness, of course. So that's what we're looking for. We're given the mass. We're also given the length times width altogether as your area. So this is your area, this is your thickness. So it's a relatively simple problem. The only thing is, you have a lot of units here. So let's work on the units. So mass, we need to convert that to grams because our density is given in grams per centimeter cubed. So we'll start with the 12.0 ounces. Put ounces on the bottom and grams on top. 1 ounce is 28.4 grams according to this. Again, punch that into your calculator. Get 340.8 grams. And I know that's not the correct sig figs, but I always round my sig figs at the very end. Next, let's look at the area. So we're given feet squared. We need it in centimeters cubed so that we can use that density. Or centimeters squared in that case, I guess. So let's do that. So we have 75.0 feet squared. Let's see. We can go from feet to inches. 1 foot is 12 inches. And then we need to square that whole thing. And then we can go from inches to centimeters. 1 inch is 2.54 centimeters, but then again square that whole thing. When you punch all that into your calculator, you get 69,677 centimeters squared. Again, I'll round at the very end. So then back to our density equation. My density was 2.70 grams per centimeter cubed. That is equal to the mass, which we figured out is 340.8 grams, divided by my area, which is length times width, 69677 centimeters squared, times my height. So you would get that the height is 0.00181 centimeters. And we're almost done, but it is asking for the thickness in millimeters instead of centimeters. So our last step here is go from centimeters to millimeters. 1 centimeter is 10 millimeters. So it's 0.00181 0.0181 millimeters. And that's our answer. Our next topic is accuracy versus precision. So accuracy means that your value agrees with the true value. Agreement with true value. Precision means that your value agrees with several measurements that you've taken. So every time you mass something, for example, you get the same value or about the same value. So this means agreement several measurements. In the lab, obviously we want to have both accuracy and precision. So we always calibrate our equipment to make sure that they are accurate. But also, we always do our experiments several times. You know, if you're doing research, you have to at least do it 3 times and those values agree with each other before you can publish a paper. And so when we do labs, if we have time, you know, if we were doing them properly, we do like 3 trials. Sometimes in a high school lab, we don't have enough time, and so we just, you know, do 1 trial and we're done. But in reality, when you're doing real science, you never just do 1 trial. So it says that 3 lab groups measured the mass of 5 aluminum bars, and each of the bars say that it's 1 mole, and this is the data that they got. We have 3 groups, group A, B, and C, and we want to know whether these are precise or accurate, or both, or neither. So in order to do that, we need to figure out what the true value is so we can figure out if they're accurate or not. So what is the mass of 1 mole of aluminum exactly? Well, we can figure that out from the periodic table. 1 mole of aluminum is 26.98 grams per mole. So then, comparing that with Group A, Group B, and Group C, let's figure out which ones are accurate, which ones are precise, which ones are neither. So comparing those values with the 26.98, we can figure out if they're accurate or not. So let's look at A. Are those accurate? Nope, they are not accurate. I'm going to use A for accurate. How about Group B? Not really. They're not accurate either. How about Group C? Are they accurate? Yep, they are accurate. Okay, how about precision? Precision has to do with whether the values that they got are close to each other or not. So Group A, they're not close to the real value, but they are close to each other. And so they are not accurate, but they are precise. Group B, they're not really close to each other, so they're not precise either. They're neither accurate nor precise. Group C, yep, they're pretty close to each other, so this is both accurate and precise. So I would want to be in Group C there. Okay, we want to also propose explanations for the patterns you see in each of the group's data. So obviously Group C is fine, but what could be something that went wrong with Group A and B? So Group A, they are precise, but they're not accurate. And in this case, they're only massing it, so it looks like, you know, our measuring device is not really calibrated. Measuring device or scale is not calibrated. Now, that would not be a good source of error, but in this case it is. You should always calibrate your equipment before you start. Okay, how about Group B? They're neither accurate or precise. Well, That looks to me like they are using different scales. When you have to compare values, you always want to use the same piece of equipment. So, for example, let's say you have a hydrate, and you want to mass it, then drive off the water, and then mass it again. You have to use the same balance for the initial and the final mass. Or if you're doing a lab where the temperature is changing, you can't use one thermometer for the initial temperature and then another thermometer for the final temperature. You have the same thermometer for both final and initial temperature. So you always want to use the same scale or the same thermometer or the same piece of equipment throughout the experiment. Okay, last thing, we want to determine the percent error for group A for bar 1. So if you remember, percent error is observed minus accepted over accepted times 100%. Let's write that down. Percent error is equal to observed, so that's what they get in the lab, minus accepted, that's our true value, divided by accepted times 100%. So for group A, bar 1, their value is 28.01 grams, minus the accepted is 26.98 grams, divided by the accepted 26.98 grams, and then times 100%. And you do not need to record the absolute value. Some teachers prefer that you do the absolute value for percent error. I prefer to keep it as positive or negative because that tells you whether your value is higher or lower than what it should be. In this case, we get 3.82%. All right, this is it for the first video. The second video, we will talk about types of matter and then also the history of atomic theory.